Okay, central limit theorem. Probably the most important theorem in all of statistics, and we have 20 minutes to cover it. Woohoo. If we don't finish it today, I'll finish it next Tuesday, and honestly, we may be able to finish this today because there isn't a ton to say. But we've been talking, we discussed the law of large numbers on Tuesday and the probability limits of y bar sub n, and now we just want to answer the question about what can we say about the limiting distribution of Sn, just the sum of a bunch of random variables. That, in general, if you just take the sum of a bunch of random variables, that's going to blow up to something with infinite variance. If you have a bunch of normals with mean mu and variance sigma squared, the sum will just lead to something with larger mean and larger variance. If you just take the simple mean divided by the number of observations, then that will be too small. As we saw on Tuesday, this will converge either in probability or almost surely to a constant. The way we want to go here is divide by the factor of square root of n. So let's say that let's take the simplest form of the central limit theorem, that you have a bunch of random variables y that are independently identically distributed with mean mu and variance sigma squared, and you define the sum of n of these things to be S sub n. The central limit theorem, which if you've taken statistics before, you probably have at least some familiarity with, says if you take the average of these things, divided by the true mean, divided by the true variance, divided by the square root of the sample size, that converges in distribution to a normal 0, 1. Or in other words, you can write the probability like that. Thing that's so remarkable about this is this works for any distribution whatsoever with finite mean and variance. Even if you don't know anything about the nature of the distribution, you start averaging stuff and it becomes normal. So, quick outline of the proof. This probably is not essential to understand, particularly if an MS student. I'm definitely not going to test you on it. If you're a PhD student, it would be worth making sure you understand this, just because my understanding is in 760 you're going to have to do this again in more generality. So let's just write Zn to be equal to square root of n times the average of the first n terms, and let where these x are just equal to the y minus the mean divided by the standard deviation. So that means that the characteristic function of this Zn is going to be equal to the characteristic function of x evaluated at t divided by the square root of n raised to the power n. So if we take logs of both sides of that, then that will give us that the limit of these characteristic functions equal to the limit of t squared times the log of that characteristic function divided by t divided by a square root of n. I had to stare at this for a minute to understand why that's true. Note that the t in the numerator and the denominator of this will cancel, and you'll end up with n times log phi of x of t over square root of n, which makes sense because log of something to the power n is just n times the log. So why are we writing it in this weird way? Well, you'll see here in a second. It makes it easier to actually calculate this limit. If we use L'Hopital's rule and let theta equal t divided by the square root of n, and assume that t is held constant, then the limit as n goes to infinity of this expression is just the limit as theta goes to 0 of that expression on the right, which, applying L'Hopital's rule, the derivative of the top is just phi prime of x theta divided by theta, or phi of x of theta divided by 2 times theta, which, after simplification, is t squared times the limit as theta goes to 0, phi prime to theta over 2 theta times phi of x of theta. Well, we plug theta equals 0 into that. We've assumed the way we've set this up, the first moment of x is equal to 0, so the derivative of the characteristic function evaluated at 0 is 0. The denominator here is also 0, so we end up with 0 divided by 0 again. So we need to apply L'Hopital's rule a second time. This time we end up with phi double prime to theta in the numerator and 2 times phi sub x of theta plus theta times phi prime sub x of theta, which evaluated at 0. Phi sub x of 0 is, of course, 1. Phi double primed of 0 is minus 1, because phi double primed of 0 is equal to I squared, which is minus 1, because here we've set this up so that the standard deviation is equal to 1. Of course, any characteristic function evaluated at 0 is equal to 1. And so that means that the limit of the log of this sequence of characteristic functions is t squared over 2, so that implies that the limit of the original sequence of characteristic functions is e to the minus t squared over 2, which hopefully you recognize as the characteristic function of a normal 0, 1 distribution. So that's quick proof that you take any distribution whatsoever that has a finite first and second moment and average the things together, divide by a square root of n, you end up with something that's normally distributed. So this is just a quick proof, partly because I don't want to torture the MS students with too much math, and partly because we're about out of time this semester anyway, and I didn't want a huge excursus on complex numbers. One way to avoid this is to use moment-generating functions to do the proof, which is the way you'll see it in a lot of elementary textbooks. The problem with using moment-generating functions, as I've noted earlier, for the moment-generating functions to exist, all moments have to exist, which is a very strong assumption that leaves out the log normal distribution. For instance, it leaves out, I think, all forms of the t-distribution. I think the t-distribution only has moments that exist up to the number of degrees of freedom. So the advantage using characteristic functions, you only need the existence of the first two moments. And if you look in the Goot book, he also does a proof based on characteristic functions, but uses Taylor's series rather than L'Hopital's rule. Whatever. Little bit on the history. It was first proved for Bernoulli random variables. Laplace described the version above, which is the simplest version of the generalized central limit theorem. Apparently, the proof wasn't quite right, but we won't dwell on that because that's definitely not going to be on the qualifying exam. So, and just in terms of vernacular, people often say things like y bar is approximately normal with mean mu and variance sigma squared over n, which is a true statement. However, it's problematic to say y bar sub n converges in distribution to mu comma sigma squared over n, because the thing on the right is not a single distribution that you can converge towards. It's a sequence of distributions. And not only is this a sequence of distributions, it's a sequence of distributions that's converging in distribution to a degenerate distribution at mu. So it's not correct to say that that's converging in distribution to the thing on the right. What you can say is that if you write the expression like this, square root of n times y bar sub n minus mu over sigma, that does converge in distribution to a normal 0, 1 distribution. The important thing is whatever you're converging to in distribution has to be some fixed thing. It can't be a sequence of distribution that's in turn converging to something else. Is there a question?
No, I was just wondering, as asymptotically as that currently
Yeah.
is it always
Well, I mean, the more probably the quote-unquote most correct way would be to say it's converging in distribution to this limit. But I mean, if you just say it's asymptotically, whatever, I mean, people will, for the most part, know what you're talking about. And like I said, that the distributions that we've seen thus far, other than the Cauchy, have finite means and variances. Almost all distributions that we care about in practice will have finite means and variances, and in which case this will apply, and you can approximate the distribution of y bar sub n with normal mu sigma squared over n. And if you don't know mu and sigma squared, which in practice, of course, you won't, then you can replace them with the sample mean x bar and the sample standard deviation, usually denoted by s. If you've taken statistics before, you know that has a t-distribution, but we're not going to get into that this class. Hopefully you'll cover it in 661. But if you don't have finite mean and variance, then all bets are off. As I mentioned on Tuesday, like you take the mean of a bunch of Cauchy random variables, for instance, and it just remains a Cauchy random variable. It never even starts to converge to a mean, and it certainly never approaches a normal distribution. If you do like the t-distribution with 1 degree of freedom, which has finite mean but infinite variance in general, the central limit theorem will not work for that either. And normal approximation can be inaccurate for certain values of n, and depending on when n is big enough for the central limit theorem to apply is hard to know. In practice, though, it's almost never an issue. I mean, the guideline I give to students in my intro class is if you have a distribution that's fairly normal to begin with, usually n equals 5 or 10, and you're already fine. If you have something that has like outliers and or some skewness, you may want to wait till like 20 or 30. If you have like the most horrible distribution you've seen in your life with extreme skewness, millions of outliers, high variance, everything that possibly could go wrong does go wrong, then you might need like 70 or 80. It's a really remarkable result, and it kicks in for relatively small sample sizes. I'll do some examples of this here in a minute. That most of these examples you'll never use in real life, given once upon a time when we didn't have computers that could easily compute the distribution function of like the binomial or the Poisson, for instance. These approximations were really handy. Nowadays, R SAS can do this just as easily, so you typically won't want to waste your time. And I mean, in general, that with modern techniques like bootstrapping and so forth, we need the central limit theorem a lot less than we used to. But I mean, that said, like, if you study like regression, all of the confidence intervals and inferences for regression coefficients and so forth basically depend on the central limit theorem. It's used in so many different areas of statistics, it's not going away anytime soon. So, simple example of this, say you have like a Bernoulli random variable and you let the sample proportion be denoted by y bar sub n. Then, using the same logic on the previous slide, if you subtract the true mean, the true proportion of success divided by the standard deviation, divided by, and that converges in distribution to a normal 0, 1. Or in other words, the sample proportion itself is approximately normal with the parameters listed on this slide. And is this useful? Well, we can compute the exact distribution of the sum in this case because we know that the sum of a bunch of Bernoullis is binomial. So we would expect the sum to be normally distributed with mean n times theta and standard deviation n times theta times 1 minus theta. To compute the normal approximation of the binomial CDF, I'll go through this kind of quickly because we're running out of time and it's fairly self-explanatory anyway. You just take the CDF of the binomial distribution, which you can calculate just by summing over the probability mass function and comparing that to the normal approximation. And I'm not using the continuity correction here, which you may have learned about if you've taken statistics before. These numbers would look even better if I had. So here's for various values of n and x, shows the true value based on the true distribution function of the binomial, and also comparing both the normal and Poisson approximations. That you can see even for very small sample sizes, neither the normal nor the Poisson is half bad, that for small sample size and small probability of success, the normal approximation's a little worse, but generally speaking, it's not drastically off. Second example, negative binomial, that you can, once again, you can think of this as being the sum of a bunch of independent geometric random variables. Using the formula for the mean and variance negative binomial, we can find the limiting distribution of the negative binomial, blah, blah, blah. And again, we can compute the true value of the CDF for the negative binomial using R, compare that to the normal approximation, and once again, it's almost identical. Little note if you're trying this at home that S plus and R, they define the negative binomial to be the number of failures before the nth success, slightly different than the way I defined it in class, although I noted that the other parameterization is sometimes used. So one last example, the Poisson. Recall for the Poisson, both mean and variance are equal to lambda. Standard deviation is therefore square root of lambda. Divide that by square root of n, that should have a normal 0, 1. Blah, blah, blah. So once again, we know the exact distribution of the sum of a bunch of Poissons. That's just a Poisson with parameter n times lambda. And the normal approximation would just be normal with n times lambda, n times lambda. Again, we can compute the exact CDF by summing over the probability of mass function, comparing that to the normal approximation, and once again, for reasonably large n, the approximation is quite good, and even when the n is fairly small, it's not drastically off, indicating that does seem to be working in general. So, very briefly in the last 5 minutes, this definitely is not going to be on the exam. This is more for statistical literacy and anything else, and I think you will prove some of these more general results in 760 if you take that, but the version of the central limit theorem that I just proved, where all the random variables are independent and identically distributed, is in practice oftentimes too restrictive, that maybe the yi's are independent but may have different means and variances, or there may not be 100% independent. So here's a couple quick generalizations of the central limit theorem. I'm certainly not going to prove this, but just so you know, these sorts of things can happen. So let's say that the random variables are independent, but their means can be different, and their variances can be different. But the random variables, they're all uniformly bounded, that they can't be bigger than some fixed cutoff m. That will be frequently satisfied in practice. Maybe, well, for instance, you give people a test with possible scores from 0 to 100. Well, the probability the score is bigger than 100 is 0, so this condition would be satisfied. And the sum of the variances has to go to infinity. The vast majority of the time that will be satisfied. Usually the only case that won't be satisfied is if your sequence of random variables is converging to a constant or something like that. If those two conditions are satisfied, then the central limit theorem still holds. and the sum of the random variables will converge to something that has a distribution with the expected value of the sum divided by the square root of the variances.
Sorry. So in your test example, it's impossible for the yi to be greater than like 100, but in number 1, it's still possible for the yi's to be greater than that. It just happens to probably be 0.
Right.
Okay, so they're technically different then, right?
Yeah. I mean, it's the same confusing thing I talked about earlier, that just because the probability of an event is 0 doesn't mean that it can't happen. That it just, like I say, if you're in 690 and you've learned about some of the measure theory stuff, you know that a lot of times some of the theorems don't hold on sets of measure 0, and we just say, since those have probability 0, we're going to ignore those. But for practical purposes, when you would use this, generally speaking, you'll know that your variable is bounded by some upper bound. And another central limit theorem holds for dependent variables that say that we drop the assumption of independence, that we can talk about this idea of M dependence, that the idea behind M dependence is that if you have a sequence of random variables and once they get sufficiently far apart, then they're independent. This is the same idea of clumpy dependence that we talked about on Tuesday, that it's common in time series data that two observations, one after another, may be highly correlated. You get far enough apart and you're independent. And if that condition is satisfied, then, and you once again have uniformly bounded random variables, then the central limit theorem still holds. That's all I have to say about that, which is good because I'm out of time. Sorry I went through this kind of quickly, but there's not that much to say. I mean, as I said, I don't anticipate that there will be many, if any, homework or exam problems on this just because it's tough to write problems about, but I go over it just because I think it's really important from the point of view of statistical literacy, be able to answer the question, well, if I take the average of my time series data, can I assume that it's normally distributed? And the answer is yes, if you assume that the observations are independent once they're far enough apart.